In this chapter, we're going to discuss all the consequences of convexity, and the first section focuses on the continuity of convex functions. So let me define the concept. A function f from Rn to the extended real line is said to be continuous at a point x bar in the domain of the function. Here, what it means is f of x bar is a real number. If for any epsilon greater than 0, there exists delta greater than 0, such that the absolute value of f of x minus f of x bar is less than epsilon whenever the norm of x minus x bar is less than delta. So this is a very familiar concept of analysis, and in this duration we look at this definition for extended real value functions. Okay, so from the definition we see the following important property. If f is a continuous at x bar in the domain of the function, then x bar actually belongs to the interior of the domain of the function f. Okay, how come this is true? The proof is very simple. For example, here we can pick epsilon equals 1 and get the following result. So for epsilon equals 1, we can find delta greater than 0 such that the absolute value of f of x minus f of x bar is less than 1 whenever x is in the open ball with center at x bar and radius delta. Okay, so from here we see that f of x is strictly less than f of x bar plus 1, and this is less than infinity whenever x is in the open ball with center at x bar and radius delta. Therefore, the open ball with center at x bar and radius delta is a subset of the domain of the function f. Okay, and this implies that x bar is in the interior of the domain of the function f. Okay, now for convex function, it is very nice that the converse is true. So I'm going to show that if x bar belongs to the interior of the domain of the function f, then f is continuous at x bar. So the converse of this statement is true, and we can prove more. That is, if x is in the interior of the domain of the function f, then the function is Lipset continuous locally Lipset continuous actually around that point. Okay, so the goal of the next part of the lecture is to prove that statement. Okay, so before continuing, I'm gonna present a very important lemma that we're gonna use later on. Okay. Let f from Rn to the extended real line be a convex function if f is bounded above on a closed ball with center at x bar and radius delta. Here it works for the open ball as well. Then f is actually bounded on this ball, on the ball with center at x bar and radius delta. Okay, so this is an illustration of this result. Now here, this is the graph of a convex function, and we can see that f is bounded above by m in the closed ball with center at x bar and radius delta here. Then f is also bounded below on this ball, and therefore f is bounded on the ball. Okay, so let me go ahead and give the proof of this lemma. By the given assumption, there exists a number m such that f of x is less than or equal to m for all x in the ball with center at x bar and radius delta. Okay, and our goal is to show that f is bounded below on this ball. So let m be the function value at x bar. So this is a real number and it's fixed. Okay, and for any u in the in the ball with center at x bar and radius delta. So this is x bar and this is u. Okay, we can always find an element x such that x bar is actually the midpoint of the line segment connecting x and u. Okay, so for any u in this ball, let x be the element defined by x bar is equal to x plus u divided by 2. Okay, so here x is defined explicitly as 2x bar minus u. Okay, so x can be given explicitly by that formula. Then we see that f of x bar is equal to f of x plus u over 2, and therefore it's less than or equal to 1/2 f of x plus 1/2 f of u by the convexity of f. So from here we see that f of u, here we can multiply both sides of this inequality by 2, and then we subtract f of x from both sides of the inequality. So we have that f of u is greater than or equal to 2 f of x bar minus f of x. Okay. And over here, we see that this is 2m. Okay. And now, from this definition of x, we can easily see that x is also in the closed ball with center at x bar and radius delta. We can easily prove that using the definition of x. Okay, so f of x will be less than or equal to capital M. Okay, so from here we will see that 2 f of x bar minus f of x is actually greater than or equal to 2m times minus capital M. Okay, and because this is true for any u in this closed unit in this ball, the function f is bounded below on this ball, and therefore it is bounded on this ball. Now I'm going to define another important concept for this section. It is called the Lipset continuity for functions. We say that the function f from Rn to the extended real line is Lipset continuous. On a subset omega of the domain of the function f, if there exists a constant L greater than or equal to 0 such that the absolute value of f of x minus f of u is less than or equal to L times the norm of x minus u whenever x and u are in omega. Here we require that omega is a subset of the domain of the function f to make sure that f of x minus f of u makes sense whenever x and u are in omega. Okay, and we say that f is locally Lipset continuous around x bar in the domain of the function f if there exists L greater than or equal to 0 and delta greater than 0 such that the absolute value of f of x minus f of u is less than or equal to L times norm of x minus u whenever x and u are in the ball with center at x bar and radius delta. Okay, so what it means here is f is Lipset continuous around x bar in the domain of the function if there exists delta greater than 0, so that f is locally Lipset continuous on the ball with center at x bar and radius delta. Okay, so next we are going to prove a very important theorem that links the boundedness of a convex function with the Lipset continuity of the function. And from this definition, we can see easily that if f is locally Lipset around x bar, then we can apply this for u equals x bar and obtain the continuity of the function at this point. Okay, and from there we can also see that x bar has to be in the interior of the domain of the function f. Okay, so now this is the theorem. Okay, let f from Rn to the extended real line be a convex function if f is bounded above on the ball with center at x bar and radius delta. Over here, delta is greater than 0. Then f is Lipset continuous. Lipset continuous on the ball with center at x bar and radius delta over 2. Okay, so now I'm going to go ahead and give the detailed proof of this theorem. Okay, so here is the ball with center at x bar and radius delta. Okay, and then this is the ball with center at x bar with radius delta over 2. Okay, so in order to show that f is Lipset continuous on this ball, we have to take any 2 points x and y in this ball and then show that x is a constant L greater than or equal to 0. So that this inequality holds for xu in the ball with center at x bar and radius delta over 2. Okay, so fix any x and u here. I fix any x and y, it doesn't matter, in the ball with center at x bar and radius delta over 2. Okay, and here we look at the case where x is different from y. Okay, and now we will define a new element u in this way. Okay, so we define u by the following formula. U is equal to x plus delta over 2 times x minus y times over here is the norm of x minus y times x minus y. Okay, so this is x and this is y, and this is the vector x minus y. So this is x, this is y, and this is x minus y. Okay, and then we divide the vector x minus y by its norm to normalize this vector. Okay, then starting from x, we move a little bit we move a little bit by using the constant delta over 2. Okay, so this is actually u, which is x plus delta over 2 times norm of x minus y times x minus y. Okay. Then, as you can see in this figure, u is still in the ball with center at x bar and radius delta. How come this is true? We can see from here. Okay. Then u belongs to x plus delta over 2 times b. Over here, b is the closed unit mole of Rn. This is true because x minus y over norm of x minus y is a unit vector. The norm of that vector is 1. So this is an element in B. So u belongs to x plus delta over 2b. Now, as you see here, x is in the ball with center at x bar and radius delta over 2. So x belongs to x bar plus delta over 2 times b. Okay, so we end up having that x plus delta over 2b is a subset of x bar plus delta over 2b plus delta over 2b, and this is actually equal to x bar plus delta b. Okay, and here it is exactly the closed ball with center at x bar and radius delta. Okay, so by defining the element u by this formula, we see that u belongs to the closed ball with center at x bar and radius delta. Okay, so for simplicity, let alpha be delta over 2 times norm of x minus y. Then u has this representation. U is equal to x plus alpha times x minus y. Okay, and from here you can see that x is a point in the line segment connecting u and y. So x can be represented as a convex combination of u and y. Okay, so from here we can write down that representation. So this is just the same as x plus alpha x minus alpha y. That is the same as 1 plus alpha times x minus alpha y. From here, we can add both sides by alpha y and divide by 1 plus alpha to have this representation of x. So x is equal to 1 over 1 plus alpha times u plus alpha over 1 plus alpha times y. Okay, and note that the sum of these coefficients is 1. Okay, by the convexity of x, of f, the function f, I'm sorry, f of x is less than or equal to, here f of x is equal to f of this, f of x is equal to f of 1 over 1 plus alpha u plus alpha over 1 plus alpha y. So by the convexity of f, this is less than or equal to 1 over 1 plus alpha times f of u plus alpha over 1 plus alpha f of y. Okay, so to have an estimate for f of x minus f of y, we subtract both sides of this inequality by f of y and have the following. Then f of x minus f of y, f of x minus f of y is less than or equal to 1 over 1 plus alpha times f of u plus alpha over 1 plus alpha f of y, and then we subtract f of y. By a simple calculation, we end up having 1 over 1 plus alpha. Here we have f of u minus f of y. Okay? Now, because the function f is bounded above on this ball, by the lemma presented earlier, f is bounded on this ball. Okay? So both the f of u, the absolute value of f of u, and the absolute value of y will be less than or equal to a constant m. So this is less than or equal to m over, actually 2m over 1 plus alpha, where m is the supremum of the absolute value of f of x, where x is in this ball. Okay, this supremum is a real number because f is bounded on this ball, and as I mentioned earlier, f of u is less than or equal to m, and minus f of y is also less than or equal to m. That's why we have this. Okay, and now from here we can use the formula for alpha here to continue the proof. Okay, so because alpha is equal to delta over 2 times norm of x minus y, we have that f of x minus f of y is less than or equal to 2m over 1 plus delta over 2 times norm of x minus y. Okay, and by a simple calculation, we see that this is just 2m times, this is 4m times norm of x minus y over delta plus 2 times norm of x minus y. And this is less than or equal to, by removing this non-negative number, we have that this element, this number is less than or equal to 4m over delta times norm of x minus y. Okay, so this is true whenever x and y are in the ball with center at x bar and they just delta over 2. So because it's true for any x and y, it's also true for any y and x. Okay, so by interchanging the role of x and y, by interchanging we see that f of y minus f of x is also less than or equal to this number. Therefore, the absolute value of f of x minus f of y is less than or equal to 4m over delta times norm of x minus y. And as we mentioned earlier, x and y are taken arbitrarily in the ball with center at x bar and they just delta over 2. And this inequality also holds if x is equal to y, because in that case both sides are 0. Okay, so this is true for all x and y in the ball with center at x bar and they just delta over 2. So we have completed the proof that the absolute value of f of x minus f of y is less than or equal to a constant L times the norm of x minus y whenever x and y are in this ball. Therefore, f is Lipset continuous on this ball.